Today, we're diving into a world where a high-grow sensor, Bluetooth, and IoT mill come together. We will set up a scenario of agriculture IoT, where we distribute multiple sensors around the garden to measure the temperature and humidity of the soil. Then, IoT Mill will extract the sensor readings using its Bluetooth gateway capabilities and send the data into the cloud. Since our sensor runs on Mongoose OS, an open-source operating system for devices in the Internet of Things realm, the plan for this video is to download Mongoose OS tool to manage the device, learn how to change the configuration parameters of the device, and finally then build and update the device with shiny new firmware. We start on the Mongoose OS webpage, which I've conveniently linked in the video description. Pick the MOS option for your operating system. In my case, it is Windows, so I just need to download and save mos.exe file. Next, let's grab the source code for our Higrow sensor project from GitHub. Check the video description for that link too. You're probably familiar with Git, right? So we'll do a Git clone into a folder named Higrow. If Git is not your thing, don't sweat it. Downloading an archive works too. But Git gives us that cool edge to track changes we will make to the configuration. Next up, open that Higrow folder in Visual Studio Code. Our target? The MOS YAML file. It needs a bit of tweaking, and I've got a customized file with helpful comments and a simpler structure. You'll find the link for that in the description too. Now let's talk about the device ID, set by btdev_name. This parameter is a game changer. It's how IoT Mill spots the right Bluetooth device and ignores all devices with the names that do not fit the pattern, and tags sensor data for cloud analytics. Think about it. In something like agriculture IoT, knowing exactly which sensor is crying out for its area to be watered is crucial. You'll find a couple more device ID parameters in there: Higrow device ID and device ID. They're like echoes of the sensor's past developer, not used by IoT Mill, but it's wise to sync them up to sidestep any future confusion. And here's the cool part: defining how we extract sensor data. You can opt for individual parameters like Higrow temperature, plus provide a name for a parameter that lists the names of all available sensors. Later on, we will configure those in IoT Mill. A better option is to send all sensor data with a single JSON structure. It's all about efficiency and saving that precious battery life. Once our configuration file is set, it's time to bring our sensor to life with a firmware update. We'll switch to the console and fire up the MOS tool right from our project directory. A heads up, it opens a new browser window connecting you to the MOS process that now keeps running in the background. Bookmark this page, since you cannot start another copy of MOS. So if you close this browser tab by accident, then you'll have to restart your computer or terminate the MOS process to get back in. In the command line interface at the bottom, we see the current directory being /demo/mos/higrow, right where we need to be. Need a change of scenery? Just type cd and the new path. And if you're curious about other commands, MOS help is your go-to. Ready for the fun part? First, pick the right controller type for our device in the menu on top of the screen, ESP32 for us. Then, we need to select the serial port for communication with the device. Once our Higrow device is connected via USB, it pops up as COM6 in the device manager. And now we can choose COM6 in the MOS management screen. You'll even start seeing debug info collected from the device on the right side of the screen. Now, the command MOS build is our magic spell. It sends our files up to the cloud, where the new firmware is crafted and sent back down to our computer. The whole show takes a minute or two. The grand finale? MOS Flash. That's our command to write the updated firmware to the device. Based on the specific version of your device, there may be a little dance to do with the buttons on the device to allow us to overwrite the existing configuration. Check the instructions. Voila! As the device restarts, watch the right side of the screen. It's like watching the heartbeat of our project, pulsing with fresh new life. And that, my friends, is how you make a Higrow sensor a part of our exciting IoT journey. All right, let's take a moment to wrap up what we've accomplished so far. We have ventured into the world of the Mongoose OS, a journey that started with us downloading MOS tool and project files for Higrow sensor from GitHub. The next step was to tweak the configuration parameters in the MOS YAML file. This way, we're tailoring the sensor to our unique needs. Then we brought the MOS tool into play. With a simple MOS build command, we crafted new firmware, a bit like baking a tech pie, wouldn't you say? But wait, there's more. We connected our Higrow sensor to our computer using a USB cable. Then came the moment of truth, using MOS Flash to update the device firmware. And the coolest part? The web interface of the MOS tool. It's like having a window into the soul of our device, allowing us to monitor and debug to see what's really going on under the hood. It's our troubleshooting secret weapon. But hold your horses, we're not done yet. In the upcoming videos, we're going to see all of this come to life. Imagine the IoT Mill, like a digital maestro, collecting sensor readings from the Higrow device via Bluetooth. Then, it sends this treasure trove of data to the cloud data warehouse for processing. Think of it as our sensor's grand performance, with data dancing gracefully to the cloud and shaping our sample agriculture IoT project. Stay tuned, because we're about to witness the symphony of technology in action. Trust me, you don't want to miss what's coming up next.